So yes, I was saying lack of parallelism is one thing, and copying data another source of the poor performance. So sort of related to that is device underuse and the memory latency. So when I said the lack of parallelism, you've got, say, your 5,000 cores. If you have 5,000 cores, you could be doing reasonably well as long as you don't need to load a lot of data from the GPU's onboard memory. Because even though it's relatively good performance, there is still a significant latency, and this is going to be, say, around 100 cycles. So the way the GPUs deal with this is that they swap out the active work they've got and they switch into another thread of execution. And they are optimized to be able to do this extremely quickly, possibly with zero overhead in some cases, I think. So what you need to, in fact, do is have many times the number of cores you've got on your hardware, many times that number of threads active at once. And so when one set of threads reaches a point where it needs to load some data and it's stalled waiting for that to arrive, the hardware can just swap that out and then instantly get on with some other useful work in another set of threads that it's running. Then there's the memory bandwidth issue. So the memory bandwidth on something like one of these GPUs is very good, but it is finite, and you will always eventually reach the limit of that. So if you are loading an awful lot of data in and doing a relatively small amount of compute on it before trying to write it back to the GPU's memory, that can hurt you. And then finally, we've got the sort of the code branches. So the way these chips work is that they have a handful of threads executing in lockstep together, and they execute exactly the same instructions at the same instant, with only the thread index differing between them. And if you have something like a branch where half the threads go one way and half the threads go the other, what the hardware will do is it will basically turn off the threads that went the wrong way down that branch and execute one part of the branch, and then those first set of threads will be turned off, and then it will go back and execute the code path for the second set. And if you have nested if conditions, you can quickly get an explosion in the number of paths through the code that have to be executed. And effectively, you'll serialize each branch, and they will not execute in parallel. So that's a source of quite bad performance. So the solutions we're going to talk about here should be relevant on most of the GPUs you'll come across in the wild at the moment, but you know, there are going to be differences in the detail between them, and not all of the solutions will be applicable to the problems you might encounter due to the nature of your code. And we'll talk about profiling, because unless you can measure the performance that you're getting, you don't know you've got a problem. And you need to have some understanding of your code and the architecture in order to say, well, okay, I've done about as well as I can there. Okay, so parallelism and getting as much as we can. So Amdahl's law is sort of a fundamental rule of thumb used to understand the performance of parallel applications. And effectively, it says that the parallel performance you've got of a piece of code is limited by the fraction of the code that is serial. And this applies in spades to GPUs. So the sort of the example you might say is if 10% of your code is serial and has to be executed in a serial way, then the best speed up you can possibly get is 10, because even if you throw an infinite number of tasks at the rest of it, you've got that serial 10% stuck executing on one thread of execution. So GPU's performance relies on using very many parallel threads, and typically you want around 100,000 or 1 million threads of executing within each kernel. So you're going to have to make some effort to expose as much parallelism as you possibly can within your algorithms. And this might force you to rewrite your code a bit, refactor it a little, or switch to an entirely different algorithm when you're trying to run on a GPU. So you know, I'm afraid there's not much general guidance I can give here, apart from you need to try and achieve this goal. You know, because it's so algorithm dependent, I can't give you a set of guidelines there. So another point is copying between the CPU's host memory and the device's onboard memory. And these separate memory spaces mean that some copying is inevitable, and you know, you just have to deal with that. And this is relatively slow because it runs over the bus connecting the CPU to the GPU. So you simply have to try and avoid any copy that is unnecessary. So you want to get your working data onto the device and leave it there, and never unnecessarily move it back to the host before and back to the device again. And sometimes this might mean that you end up doing some extra calculation instead of communicating some data. And that's fine. Compute is relatively cheap these days compared to moving data. And you might also end up having to move more code than you want to onto the GPU. For example, you might have a large code base, and perhaps only 10% of this is in the performance critical regions. But if some of that other code in the rest of the application needs to use data that is held on the GPU, you may end up having to port a lot more of that than you might initially expect to the GPU in order to avoid this unnecessary copying. So, for example, this little snippet of code shows a common pattern. So you've got some number of time steps you need to do to advance your simulation forwards. So you might do a cheap operation on the host, and then copy it into the device, run your kernel that does the main meat of your work on the GPU, and then copy that data from the GPU back to the host and do your cheap host operation. So you're going to have to refactor this, and you're going to have to take your kernel and refactor it to run on the GPU. And hopefully that's not going to be too unpleasant for you. Okay, so occupancy and latency guiding. So we talked about the fact that the memory latency on a GPU is significant, and the way to deal with this is to throw a lot more work at the GPU. So by splitting the work up and distributing it over the threads on the device, you might initially think that you want the number of threads to be equal to the number of cores. But like I mentioned before, you actually need a lot more than this because of the latency being, say, 100 clock cycles. And the hardware can swap out one of the stalled threads and swap in one that's ready to run and get some useful work done while the hardware waits for that data to arrive. So suppose we've got a 2D loop going over, say, an image of 512 pixels along each dimension. So were we to parallelize the inner loop only, we would have 512 threads active at once, and for CPU-based threaded programming, that would be an awful lot of threads. But this is going to be relatively poor occupancy on something like a modern Volta GPU, using only 1/10 of the hardware. But if we parallelize both of them, we've got 250,000 threads going, and that is much more like it. You're going to start to see the advantage of the hardware here. So caching. So if you recall Kevin's first talk, he talked a lot about the cache on the typical CPU architectures and how there's multiple levels, and a large fraction of the die space on these chips is devoted to managing this. So if you have an array of data and you're programming in C, for example, then you know that the rightmost index, if it's a conventionally laid out array, is the one that varies fastest. What that means is that if you were to move one element through your contiguous linear array, that right index would be changing the fastest as you move through the full array. So a change of 1 in that last index will mean a change of 1 in the linearized address of your array, whereas if you were to change the one of the left towards the left, sorry, indices, you would move forwards by a large jump in the contiguous memory of your data. And in Fortran, Fortran works the other way around. So the leftmost index runs the fastest. And when you take your threads, if you were to run this across threads, you want each thread to have consecutive memory access. So GPUs have a very high peak memory bandwidth, but they can only reach this when the memory accesses are coalesced. And what that means is that when consecutive threads within your GPU access consecutive memory locations, and if not, performance access is going to be serialized and give you poor performance. So what does that mean? That means that when the threads try and read a bit of memory from the device's global memory, what will happen is that the hardware that's attached to the SM, the streaming multiprocessor that they live on, will take all the outstanding memory reads or writes, and it will try and coalesce them into a smaller number. And it can only do this if the threads are reading a chunk of memory in order. So for example, if you have 32 threads on your block and they all want to read one integer, then it can coalesce that into a single request and issue it and get it back. But if each thread is reading from a different part of the array, it will have to effectively issue 32 of these memory requests and wait for all of them to be serviced before it can move past that instruction in the code. So we need to think about what is the correct order. So in one dimension, it's nice and simple. If you compute, so let's say your threads per block is some number and then with 1 in the Y and Z directions. Consecutive threads are those with consecutive indexes. And in C, this is nice and simple. You compute your sort of global index in the way that Kevin showed before lunch. So you take your block index, scale it up by the size of the block dim, and then you add on each thread's local index that. And then you can say your output is some function of some input at that exact index. And in Fortran, it's much the same, except you've got to remember to subtract 1 because Fortran counts from 1. And both are great, but access is coalesced in both cases. So if we're doing a 2D array, let's talk about C first. So again, the rightmost index runs fastest. So if we compute I from the block index's X coordinate, that's going to be bad because each, and then we're running a loop over J. So each individual thread is running that for loop, and so each thread will run for one value of I and for all the values of J. So that means that at one moment when it issues the request for data, you're going to have multiple threads requesting for strided access through your data array. And that will give you quite poor performance because you'll have to wait for all 32 of them of those memory reads to have completed before you can get past it. Whereas if we use the thread index to compute the J index, this is going to give us good performance because the consecutive threads are accessing contiguous elements in our data array. because each time around the for loop we are dealing with one, I can never remember if it's a row or a column of the data, but that will ensure that the threads are accessing contiguous elements. Okay, so in Fortran, remember it's the leftmost index that runs fastest. So the bad case is when you use the thread index to compute the J value here. So again, it's exactly the same as before. We are have consecutive threads are accessing elements that are nj elements apart in the data array. Whereas if we use the thread index to compute I, that's going to be good. That's going to keep the hardware happy. So that was just for a one-dimensional decomposition, which we've already said is not quite optimal because we're only having, say, 512 threads available. This would have, we need to decompose it so each thread is dealing with a single pixel or element in our 2D array. So let's try doing this this case. So we're saying our blocks per grid is some number in the x direction and some number in the y direction, and the threads per block is exactly the same. We're having a little tile within our bigger image being dealt with by each block. So for dealing with the mapping from a three-dimensional thread index to a linear thread index, CUDA goes with the Fortran convention. It has x counting fastest, then y, and then z. So if you're writing in C, you need to compute, you need to effectively transpose the I and j coordinates from the x and y coordinates. So for example, we're computing j from the block index, the thread index is x components, and I from the y components. And then we can say that the output is at ij is some function of the input at ij, and this will be more optimal. And in Fortran, it looks much more natural. Just got to remember to subtract 1 because Fortran counts from 1, but you can just compute your I index from your x, the x part of your threads, and the same for j and y. And then the actual kernel code is exactly the same. So it's a small advantage to Fortran here. You'll notice that the slides have I and j and x and y here to try and distinguish between these two coordinate systems to avoid any confusion about computing, for example, your index is xy from your thread index xy, and you're getting into a pickle of confusion there. So that's a useful thing to remember for yourself. Okay, so code branching. So threads are scheduled in these little groups of 32, which is called a warp. And well, until Volta came along, this slide was 100% correct. But threads were scheduled in groups of 32, and they share the same scheduling hardware within the SM. And the warp executes its instructions in lockstep, and this is called single instruction, multiple thread, as opposed to single instruction, multiple data that you might be aware of from CPU program, which is your fancy vector intrinsics that Intel CPUs and AMD CPUs offer these days. So any branch in your code can cause serialization because all threads end up having to execute all branches that have at least one thread doing them, and they either throw away the irrelevant results or they just are silently turned off while those instructions execute. So you need to try and avoid this so-called warp divergence. So imagine we need to split a thread up into two groups. So let's say we compute our local thread ID from our local index from the thread ID's X part, and we're saying if the thread ID is even, do something, and if it's odd, do a different thing. So within a block, we're guaranteed that half the threads are going to do the first thing and the other half will do the second thing. So we have the runtime of the total thing will be increased because it has to execute both branches always. So what you might be able to do is rearrange your data in some way to ensure that threads in the same warp follow the same path. And we're using this internal variable warp size. So we're making our global index in the same way, and we're saying that if the thread ID divided by the warp size has no remainder, sorry, is even, we'll do one thing, otherwise we'll do a different thing. So this ensures that threads 0, 1, 2, 3, up to 31 inclusive do another thing, and 32 and so on will do the other. And this will ensure that each warp as it runs through the code will not be stalled waiting for bits on the other side of the if statement to work. Okay, so some performance problems. So the compiler can give you some clues if you've got a bit of code that's either you're not sure about or is running a bit slower than you might have hoped. You can tell the compiler to be verbose when it's creating the PTX assembly, that stage of the compilation process. So it will report lots of things like the register usage, the use of constant shared memory, which Kevin will mention a bit. It will tell you if registers are being spilled into global memory, which is something that's extremely harmful to performance. So the registers are the little pieces of memory right next to the core, and they can be accessed with no overhead at all. So if the compiler runs out of space in the register file, it will resort to storing some of that data into global memory, and then so your code will try and read from a register, but it will actually have to go off and fetch data from global memory, and that will really hurt your performance. And this can be useful to use during development, and you can tinker around with a little bit of micro optimization to try and reduce the register usage, and that can have actually quite a big effect on performance if you can do it. And then profiling. So the command line profiler mvprof is okay. It gives a traditional text report on which bits of code took what fraction of the execution time and so on. There's also the visual profiler, which is really quite good. I think it's changed its name now. Kevin, is it now Nsight in the CUDA 10? Is that? Yeah. So I've not used the new 10 version, but yet. So that's to be looked at. But certainly the visual profiler was quite good, and I would expect that Nsight will be better, if not at least as good. The NVIDIA documentation is quite good on these things, and they usually have some nice blogs showing off how to use it. So, okay, so I know I've dumped quite a lot of information on you here, but if you pay attention to these sort of basic rules of thumb, you can get a fairly decent fraction of peak performance on actual real code. For example, you can easily get 50% of peak performance on using CUDA, and doing that on a CPU would be quite an astounding feat. But the corollary of that is that not all problems will necessarily run well. Sometimes there is just not enough parallelism in your problem. You might think you've done well to get a factor of 10 or 100 of parallelism in it, but that is not going to be sufficient on a GPU to get the best out of the hardware. So that's the end of these slides. So I'd like to ask for any questions on this before we talk about the exercise. Yes, Mark has a question.
I was wondering if there's a similar kind like MPI W time. Is there something equivalent in OpenMP?
OpenMP, yes. There's OMP I forget the name of the call. I don't know if CUDA has a particular time one. I think they just assume you'll use your, for example, from the C++ library, std chrono, whatever. Std chrono high resolution timer, for example. Okay, so for the exercise, no, that's not the right one, sorry. In the exercises directory, you'll find second one. If I can just get my SSH connection open again. Yes, okay, so in the GPU course exercises folder, there's one on CUDA optimize. And this is a sort of walkthrough on doing several of these steps we've talked about, measuring the performance benefits of each, and then seeing how you're doing. So you need to choose whether you're doing C or Fortran. I'm sorry, any Fortran programmers, I'm definitely not one of you. You have a main file, reconstruct, and another one with the kernels in it. And inside the source are some comments. Oh, Kevin, am I getting this wrong? Have I got confused with the other exercise? They're not inside the...
I think the README MD file has got lots of information.
Yeah, it should, but... Oh, it's because my terminal's gone weird for some reason. But yes, the README has plenty of information about what you need to do. Run the original to get you started, and so on. So let you get cracking on that, and Kevin and I will be online here to assist with any questions as you get stuck. Thank you.